Okay, this video is going to lay the groundwork for the examples we're going to work in class related to limits at infinity. And so the motivation for this whole section, and kind of one of the big reasons we study limits at infinity, is to talk about the shapes of graphs and what happens to graphs as x gets large. Another reason we might think about studying limits at infinity deals with a lot of applications. So if you have a function or a way a population or something is behaving, you may be really interested in seeing what happens, right, as time goes on for forever. And so things at limits at infinity are actually really something that is important and interesting. So really quickly, the motivation for all of this, one motivation, right, is sort of thinking about graphs of functions. And so if you think about a function, it can have two kinds of what are known as asymptotes. It can have vertical asymptotes, so maybe something that looks like this, where there's like an invisible line here, like at x equals 1, where the function is getting really close to that line, but not touching it. And so that's a vertical asymptote. And the way we find that, there are places where the limit as x approaches some a of our function equals plus or minus infinity or does not exist, in the sense that one thing goes to infinity and the other goes to negative infinity. That sort of does not exist. So those are the kinds of places that we're looking, or the things that we're looking for when we talk about a vertical asymptote. Right? Any place where your function, the limit at its particular a value, is going to infinity, which we talked about in another section, but we didn't call it an asymptote. Mainly there are places where you have a 0 in the denominator, but not in the numerator. Or functions that have a restricted domain. So something like ln of x, right? It has a vertical asymptote at 0 because of the fact that it stops at a certain spot. So those are the kinds of things that we're talking about when we talk about a vertical asymptote. And then a horizontal asymptote, this picture that I drew actually also has a horizontal asymptote. That's something here along the x-axis, or some kind of y equals something, in this case y equals 0, where the function is getting really close to that line as x gets big, but not touching it. So this is places where the limit as x approaches plus or minus infinity of f of x equals a particular number. So if it equals a number, then we're going to say that that has a horizontal asymptote of whatever that number is. So for example, we'll look at some examples here in a minute, but that's the idea. So you take the limits as x goes to plus and minus infinity. And then if you get a number, then you have a horizontal asymptote at y equals that number. Okay, so that's the idea of these two things. So we have vertical asymptotes, which are x equals a number, okay, and the number comes from this sort of a value if there's an infinite value for the limit. And then there are horizontal asymptotes where you're taking the limit at infinity and seeing how you get back a number. So they're kind of like the opposite concepts, which is why you get both horizontal and vertical asymptotes. We're going to look at the definitions now of our basic limits that go to infinity. So we've taken limits at infinity, and we're also now looking at limits that go to infinity. So here are some definitions of what happens as x approaches a. So the limit as x approaches a of f of x equals infinity if the values of f of x can be made as large as we please by taking x sufficiently close to a. And that has a similar definition for negative infinity. And I think we talked about that one in a previous section. So I think we've actually already talked about what happens if we get infinity as our limit. The new one here is if you have a function that's defined on some particular interval from a and then continuing on for quite some time, the limit as x approaches infinity of a function is L if values of f can be made as close to L as we like by taking x sufficiently large. And you can make a similar definition for negative infinity. So this is sort of the new idea. And then just as a note, we'll say that x goes to infinity is equal to infinity if we have a function who's getting really large as x becomes large. And so in terms of visualizing these three things, again, the first one we're talking about some value a, and we're looking at the function as it gets close to a and saying that as the function gets close to a, it's getting close to infinity. So this is f of x, and it's going up to infinity. So this is a limit of sort of the idea of number one. Number two, the idea there is we're now looking on the x-axis, what happens to our function, right, as x gets really large. So in this case, as x gets really large, right, this function is actually sort of coming to this certain point, maybe x equals, or y equals -1. So maybe this is going to -1 as x goes to infinity. Okay, so those are kind of the two ideas, and the third one is even somewhat interesting as well, where you have as x gets big, the function gets big, right? So this is as x gets big, goes to infinity, the function is also getting really big. So that's the third idea, right, that you could get really large as x gets large. So those are now, we have all that different ideas of infinity, both infinity as the equal, after the equal sign, or infinity as the thing, the x value, right, that we're interested in as approaching. And these are the definitions that help us think about what those things are. So I wanted to draw some of the basic ones that we'll be talking about and using so that we have a sense of those, and then we'll actually work our examples in class on Friday. So this is more just the base, sort of the baseline, and then we'll actually do examples and talk about how to use this in class. But I want to draw some of the more familiar functions that work with this, these sort of asymptote questions. So we'll start with arctan of x, and that's a function that many of you may not remember exactly what it looks like, but remember it's just sort of tangent of x turned on its side. And so if I was going to draw it, it would look something sort of like this, right? It's that piece of tangent of x that's between pi over 2 and negative pi over 2. So this is pi over 2, and this is negative pi over 2. And so this is an example of a function that has two horizontal asymptotes, because the limit as x goes to negative infinity of arctan is equal to negative pi over 2, and then as it goes to positive infinity, we get pi over 2. So we can write that similar. So this one down here has the negative sign. I don't know if that was clear when I first wrote it, but limit as x goes to positive infinity of this arctan is going to be positive pi over 2. So this is one that has two horizontal asymptotes, one sort of in each direction. That's why it's always really important to check both the positive and the negative infinity to see if that it might actually split and have two different horizontal asymptotes. Sometimes you get the same horizontal asymptote, but this is a really great example of one where you get two different ones. The next function that we'll draw out is tangent of x, which is really just arctan turned on its side, but you'll note that it has quite a few, instead of horizontal asymptotes, has quite a few vertical asymptotes. And these are actually drawn in a few times throughout this picture. And so here, instead of horizontal asymptotes, we actually get vertical asymptotes. And we get vertical asymptotes, quite a few of them. So our vertical asymptotes, these are at x values, right? So we'll have some things like x equals pi over 2, you could say negative pi over 2, and in fact, it's really at any pi over 2, so you could write out a nice little way to write that, something like x equals pi over 2 plus 2k, where k is an integer, or something like that. Right, so it's all the pi halves are where those vertical asymptotes are going to occur. So that's one that has a vertical asymptotes. Now we look at something like e to the x, which goes through this point here, to like either one. So it's something like this, I believe. So I'm going to draw that graph like something like this. And so this is something that has, again, there's a horizontal asymptote, And for horizontal, these lines right here, this is at y equals 0. So you take the limit as x goes to infinity, you'll get, of e to the x, negative infinity, sorry, you'll get 0. X goes to negative infinity, you'll get a 0, which is why you get a horizontal asymptote right there at y equals 0. Okay, the next function we want to look at is natural log of x, which looks something like this. And that one has no horizontal asymptotes, but it does have one vertical asymptote, and that is at x equals 0, right? At this x value, this function gets really close to the x value, but doesn't actually touch it. Another thing you can look at, right, is that the limit as x approaches 0 from the right of our ln of x is equal to infinity, or negative infinity, actually. So that's what gives us that vertical asymptote there. Last but not least is the 1 over x function, which looks something like this. And hopefully you all recognize now, after seeing these things, that this has a horizontal and a vertical asymptote. So we have a horizontal asymptote at x equals 0, or sorry, y equals 0, horizontal. Vertical asymptote at x equals 0. And again, you could do that by taking limits of 1 over x as x gets really large. Also just by looking at that picture. One thing to note with these asymptotes, for vertical asymptotes, those are asymptotes that you get really close to, right, but never actually touch. So you don't want to cross over a vertical asymptote because it's a place that your function is generally not defined. But for horizontal asymptotes, it's really the places that what happens is your function gets really large. So if something were to cross the horizontal asymptote early, that's actually not a problem because you're really interested in seeing what happens in the long term and out toward the ends. So horizontal asymptotes don't mean a lot in the early stages of the function. Vertical asymptotes mean something for the entire function because it's at one specific point that we have a problem. Okay, I want to talk about one more thing so that we have all the kind of background behind us for class tomorrow or for Friday. This is one more thing about taking the limits as x gets really large of functions where x to the n, where n is a positive integer. Or I guess positive doesn't have to be an integer actually, just n is any positive number. And also the limit as x approaches infinity of x to the negative n, where n is positive, which means you're putting it back into the denominator. So as x gets really large, x to the n, I would hope that you would imagine this raising x to a really positive number. So a positive number, and then x is getting large. So if x is getting large and raising it to a positive exponent, I hope that you would agree that this is also getting really large. So that limit's always infinity. And then similarly, here as x goes to infinity, x to the negative 1 over x to the n. That means this bottom part is getting really big. So 1 divided by really big numbers is going to go to 0. And so those are two things to think about as we think about limits at infinity. And what we're going to study is thinking about rational functions in general. And so what happens if we want to take the limit as x approaches infinity of some, f of x divided by g of x, where they're both polynomials. How do we calculate that limit, and what are our techniques to do that? So that's what we'll focus on in class on Friday, is learning how to do those processes and thinking about how to use these two limits here to do that.